length increases from CF to CI. Methods of preparation. From alcohols. Alkyl halides can be prepared from alcohols as shown in the chemical reactions. There are various ways to produce alkyl halides using thionyl chloride, and is quite convenient method as the other products SO2 and HCl are gases and are easily expelled during the distillation, leaving behind pure alkyl chloride. Methods of preparation. From hydrocarbons. By free radical halogenation. The reaction of a halogen with an alkane in the presence of ultraviolet light or heat leads to the formation of alkyl halide or haloalkane. By electrophilic substitution, aryl halides can be prepared by re-electrophilic substitution of arenes with halogen in the presence of Lewis acid catalysts such as iron or iron 3 chloride. In the presence of Lewis acid catalysts such as iron or iron 3 chloride. Methods of preparation. Sandmeyer's reaction. When an aromatic amine dissolves in aqueous mineral acid treated with sodium nitrate, a diazonium salt is formed. The formed solution is mixed with cuprous chloride or cuprous bromide, which replaces the diazonium group by Cl or Br. If we replace the diazonium group by iodine, then instead of using cuprous halide, we use potassium iodide. Methods of preparation. From alkenes. Addition of hydrogen halides. Alkene is converted to specially alkyl halides by reaction with hydrogen halide. Addition of halogens. On mixing bromine in CCl4 to an alkane, it results in the formation of Vic dibromide. Methods of preparation. Halogen exchange. Alkyl iodides can be prepared by reacting alkyl chloride bromides in the presence of dry acetone. This reaction is also called as Finkelstein reaction. The alkyl fluoride can be prepared by Swartz reaction, in which alkyl chloride bromide are heated in the presence of metallic fluoride. Halogen exchange. Physical properties. In pure form, the alkyl halides are colorless, and bromides and particularly iodides develop color when exposed to light. Melting and boiling points. Due to the polar nature and high molecular masses as compared to the corresponding hydrocarbon of organic compounds, the intermolecular forces of attraction that are dipole-dipole and van der Waals are stronger than the organic halogen compounds, due to which the boiling point of chlorides, bromides and iodides are higher than the hydrocarbons of approximately an equal molecular mass. For the alkyl group, say R, the decreasing order of boiling point of alkyl halides are Ri has the highest boiling point, followed by Rbr, then Rci, and then Rf. Melting and boiling points. For isomeric alkyl halides, the boiling point decreases with branching. This is because branching of the chain decreases the surface area and consequently the intermolecular forces of attraction. The boiling points of isomeric dihalobenzenes are nearly the same. The melting points of isomeric dihalobenzenes are quite different. The melting point of the para-isomer is roughly 70 to 100 degrees higher than the melting point of ortho and meta-isomers. The higher melting point of the para-isomer is due to its symmetrical structure, which makes it to fit better in the crystal lattice. Density. Alkyl chlorides are generally lighter than water, whereas bromides and iodides are heavier. The densities are in the order Ri greater than Rbr greater than RCl. Polychlorides are, however, heavier than water. Solubility. The halogen alkanes are only slightly soluble in water. To dissolve alkane in water, energy is required to break the bonds between haloalkane molecules and water molecules. When bond is formed between haloalkane and water molecule, then very less energy is released, due to which haloalkanes are slightly soluble in water. Haloalkanes are soluble in organic solvents such as ether, alcohol and benzene because the energy released and required are the same. Did you know? Haloalkanes are used as flame retardants, fire extinguishants, refrigerants, propellants, solvents and in pharmaceuticals as well. Many halocarbons are serious pollutants and toxins. For example, chlorofluorocarbons lead to the depletion of the ozone layer over Antarctica. Haloalkanes are the compounds which have the general formula Rx, where R is an alkyl or substituted alkyl group and X is halogen, F, Cl, Br or I. Haloarenes are compounds containing halogens attached directly to an aromatic ring. In common name system, alkyl halides are named by naming the alkyl group attached to the halogen and adding the name of the halide. In IUPAC system of nomenclature, alkyl halides are named as halogen-substituted hydrocarbon. Alkyl halides can be prepared from alcohols, hydrocarbons and by halogen exchange. The boiling points of chlorides, bromides and iodides are higher than the hydrocarbons of approximately equal molecular masses. The boiling points of isomeric dihalobenzenes are nearly the same. The melting points of isomeric dihalobenzenes are quite different. The halogen alkanes are only slightly soluble in water.
Introduction.
Father, what is the full form of LPG?
What are you doing?
I'm studying hydrocarbons. Our teacher has asked us to read about hydrocarbons.
Oh, that's good. Do you need any help?
Yes, I'm reading but not able to understand.
We use kerosene oil for domestic use. Petrol, diesel and CNG are used in automobiles. All these fuels contain hydrocarbons. Isn't it interesting?
Very interesting. Please tell me more about hydrocarbons.
Sure. Come, let's start. Objectives. At the end of this lesson, you will be able to define hydrocarbons, understand the classification of hydrocarbons, explain alkanes, name hydrocarbons according to IUPAC system of nomenclature, recognize and write structure of isomers of alkanes, learn methods to prepare alkanes, write the physical and chemical properties of alkanes, explain the conformations of ethane. Definition. Hydrocarbons, composed entirely of carbon and hydrogen, are the most important family of organic compounds. The organic compounds of simplest composition and may be considered the parent substances from which all other organic compounds are derived. The hydrocarbons are conveniently classified into two major groups: open chain and cyclic. Open chain compounds containing more than one carbon atom. The carbon atoms are attached to each other to form an open chain. The chain may carry one or more side branches. In cyclic compounds, the carbon atoms form one or more closed rings. The two major groups are subdivided according to their chemical behavior into saturated and unsaturated compounds. Classification. Depending upon the types of carbon-carbon bonds present, hydrocarbons can be classified into three main categories: saturated, unsaturated, and aromatic hydrocarbons. Saturated. Saturated means that each carbon is bonded to four other atoms through single covalent bonds. Hydrogen atoms usually occupy all available bonding positions after the carbons having bonded to each other. Unsaturated. Unsaturated hydrocarbons contain either double or triple bond. Since the compound is unsaturated with respect to hydrogen atoms, the extra electrons are shared between two carbon atoms, forming double or triple bonds. Aromatic hydrocarbons. Aromatic hydrocarbons are a special type of cyclic compounds. We can construct a large number of models of such molecules of both types, open chain and closed chain, keeping in mind that carbon is tetravalent and hydrogen is monovalent. Alkanes. Hydrocarbons which contain only single bonds are called alkanes. They are called saturated hydrocarbons because there is a hydrogen in every possible location. This gives them a general formula CnH2n plus 2. The first four alkanes are methane, ethane, propane and butane with the Lewis symbol as shown. Alkyl groups. An alkyl is basically an alkane minus one of its hydrogen atom. For example, if methane removes one hydrogen, we will get methyl. Similarly, if ethane removes one hydrogen, we will get ethyl. IUPAC system of naming alkanes 1. The IUPAC, International Union of Pure and Applied Chemistry, is composed of chemists representing the national chemical societies of several countries. One committee of the IUPAC, the Commission on Nomenclature of Organic Chemistry, has set a system of naming organic compounds. The last syllable in the name of compound designates the family to which it belongs. The alkanes all end in -ane. IUPAC rules for naming the alkanes. Number 1. The name ending for all alkanes and cycloalkanes is -ane. Number 2. The parent chain is longest continuous chain of carbons in the structure. For example, the branched chain alkane is regarded as being made from the following parent: CH3, CH2, 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 CH3 by replacing an H on the third C from left with CH3. Number 3. The carbon atoms of the parent chain are numbered starting from whichever end of the chain gives the location of the first branch, the lower of two possible numbers. For the example, given the correct direction is from left to right. IUPAC system of naming alkanes part 2. Number 4. Name each branch attached to the parent chain according to alkyl groups. In this case, the branch would be methyl. Number 5. Attach the name of the alkyl group to the name of the parent as a prefix. Place the location number of the alkyl group in front of the resulting name. In this case, it would be 3-methylhexane. Number 6. When 2 or more groups are attached to the parent, name each and locate each with a number. The alkyl substituent names are assembled in alphabetical order. Always use hyphens when separating numbers from words. The following is poethyl to methylheptane. Number 7. When 2 or more substituents are identical, use prefixes such as di for 2, tri for 3, tetra for 4 and specify the location of every group. Always separate a number from another number in a name by a comma. The following is 2,4 dimethylhexane. Number 8. When identical groups are on the same carbon, repeat the number of the carbon in the name. The following is 2,2 dimethylheptane. Number 9. Sometimes you may need to go around corners and zigzag to find the longest parent chain. The following is 3,4 dimethylheptane. Preparation of alkanes Part 1. Decarboxylation. Decarboxylation means removal of CO2 from molecules having COOH group. Saturated monocarboxylic acid, salt of sodium potassium on dry distillation with soda lime gives alkane. Wood's reaction. A solution of alkyl halide in ether on heating with sodium gives alkane. By reduction of alkyl halides. Alkyl halides on reduction with nascent hydrogen form alkanes. Preparation of alkane Part 2. By hydrogenation of alkanes. Sabatier and Sanderen's method. Alkenes and alkynes on catalytic hydrogenation gives alkanes. Kolbe's electrolysis method. Alkanes are formed on electrolysis of concentrated aqueous solution of sodium or potassium salt of saturated monocarboxylic acids. Electrolysis of an acid salt gives symmetrical alkane. However, in case of mixture of carboxylic acid salts, all probable alkanes are formed. Physical properties of alkane. State. Number 1. All are colorless and possess no characteristic odor. Number 2. Lower alkanes C1 to C4 are gases. Middle one C3 to C17 are liquids and higher are solids. Number 3. The boiling point of alkanes increases with increase in molecular weight due to increase in van der Waals forces with increase in molecular weight, that is, boiling point order. Pentane is less than hexane is less than heptanes. Number 4. Also the branching in alkanes gives a decrease in surface area as the shape approaches to spherical, which results in decrease in van der Waals forces. That is why boiling point of isomeric alkanes whose order is pentane is greater than isopentane is greater than neopentane. Number 5. The melting points of alkanes do not show a regular trend. Alkanes with even number of carbon atoms have higher melting point than their adjacent of odd number of carbon atoms. Melting point order is propane is less than ethane is less than methane. Number 6. The abnormal trend in melting point is probably due to the fact that alkanes with odd carbon atoms have their end carbon atom on the same side of the molecule and in even carbon atom alkane, the end carbon atom on opposite side. Thus, alkanes with even carbon atoms are packed closely in crystal lattice to permit greater intermolecular attractions. B. Density. The density of alkanes increases with increase in molecular weight and becomes constant at 0.76 gram per milliliter. Thus, all alkanes are lighter than water. C. Solubility. Number 1. Alkanes being non-polar and thus insoluble in water but soluble in non-polar solvents. Example, C6H6, CCl4, ether, etc. Number 2. The solubility of alkanes decreases with increase in molecular weight. Number 3. Liquids. Alkanes are themselves good, non-polar solvent. Chemical properties of alkanes Part 1. Alkanes are quite inert substances with highly stable nature. Their inactiveness has been explained as: Number 1. In alkanes, all the carbon-carbon and carbon-hydrogen bonds being stronger sigma bonds and not influenced by acids, alkalis, oxidants under ordinary conditions. Number 2. The carbon-carbon completely non-polar and carbon-hydrogen weak polar bonds in alkanes are particularly non-polar because of small electronegativity difference in C 2.6 and H 2.1. Thus, polar species, that is, electrophiles and nucleophiles, are unable to attack these bonds under ordinary conditions. In spite of less reactive nature, alkanes show some characteristic reactions. Oxidation. Oxidation of alkanes gives different products under different conditions. Alkanes are heating in the presence of air or dioxygen are completely oxidized to carbon dioxide and water with the evolution of large amount of heat. Higher alkanes on oxidation in presence of manganese acetate give fatty acids. Incomplete oxidation of alkanes in limited supply of air gives carbon black and carbon monoxide. 2CH4 plus 3O2 gives us 2CO plus 4H2O. CH4 plus O2 gives us C plus 2H2O. Chemical properties of alkanes 2. Substitution reactions. Number 1. Substitution in alkanes shows free radical mechanism. For mechanism, see free radical substitution. Number 2. Following substitution reactions in alkanes are noticed. Halogenation. Number 1. Replacement of hydrogen atom of alkane by halogen atom is known as halogenations. Number 2. Halogenation of alkane is made on exposure to halogen plus alkane mixture to ultraviolet light or at elevated temperature. Number 3. The extent of halogenations depends upon the amount of halogen used. Isomerization. Number 1. The process of conversion of one isomer into other is known as isomerization. Number 2. Straight chain alkanes are heating with AlCl3 plus HCl at about 200 degrees centigrade and 35 atmospheric pressure are converted into branched chain alkanes. Chemical properties of alkanes Part 3. Aromatization. Number 1. The process of conversion of aliphatic compound into aromatic compound is known as aromatization. Number 2. Alkanes having 6 to 10 carbon atoms are converted into benzene and its homologous at high pressure and temperature in presence of catalyst. Dehydrogenation. Alkanes are dehydrogenated on heating in presence of catalyst to produce corresponding alkenes. Pyrolysis. Number 1. The decomposition of a compound on heating in absence of air is known as pyrolysis. Number 2. The phenomenon of pyrolysis of alkane is also known as cracking. Number 3. Alkane vapors on passing through red-hot metal tube in absence of air decompose to simpler hydrocarbons. The product formed during cracking depends upon A. Nature of alkane, B. Temperature and pressure, C. Presence or absence of catalyst. Here is the example of cracking. Conformations. The different spatial arrangements that a molecule can adopt due to rotation about sigma bonds are called conformations, and hence conformational isomers or conformers. The study of the energy changes that occur during these rotations is called conformational analysis. This is important because the structure of a molecule can have a significant influence on the molecular properties, including dictating the outcome of a reaction. Although the ideas are developed for the simplest functional groups, the alkanes, the same principle can be expanded and applied to other functional groups. For alkanes, various conformations can be represented by using dash wedge notation in a structural perspective drawing. An alternate depiction is a Newman projection, which views a molecule by looking down at CC bond axis, showing the relative orientation of groups of the two carbon atoms. Conformational analysis of ethane. Conformational analyses are assisted greatly by a representation of molecules in a manner different to skeletal structure. A representation of a molecule in which the atom and bonds are viewed along the axis about which rotation occurs is called a Newman projection. In a Newman projection, the molecule is viewed along an axis containing two atoms bonded to each other and the bond between them, about which the molecule can rotate in a Newman projection. The substituents of each atom composing the bond, be they hydrogen or functional groups, can then be viewed both in front of and behind the carbon-carbon bond. Specifically, one can observe the angle between a substituent on the front atom and a substituent on the back atom in the Newman projection, which is called the dihedral angle or torsion angle. In ethane specifically, we can imagine two possible extreme conformations. In one case, the dihedral angle is 0 degree and the hydrogens on the first carbon line with or eclipse the hydrogens on the second carbon. When the dihedral angle is 0 degree and the hydrogens line up perfectly, ethane has adopted the eclipsed conformation. The other extreme occurs when the hydrogens on the first carbon are as far away as possible from those on the second carbon. This occurs at a dihedral angle of 60 degree and is called the staggered conformation. The staggered conformation of ethane is more stable than the eclipsed form by 12.1 kJ per mole, so that as one methyl group rotates 360 degree relative to the other, the compound passes through three stable staggered conformers via three unstable eclipsed forms. This barrier is small enough that at 25 degrees Celsius, the compound changes conformation about 50 million times each second. Sawhorse projection. Sawhorse projections are very similar to Newman projections, but are used more often because the carbon-carbon bond that is compressed in a Newman projection is fully drawn out in a sawhorse projection. When properly laid out, sawhorse projections are useful for determining enantiomeric and diastereomeric relationships between two molecules because the mirror image or superimposability relationships are clearer. Like with the Newman projections, a sawhorse projection is a view of a molecule down a particular carbon-carbon bond, and groups connected to both the front and back carbons are drawing using sticks at 120 degree angles. Sawhorse projection can also be drawn so that the groups on the front carbon are staggered 60 degree apart or eclipsed, directly overlapping with the groups on the back carbon. Below are two sawhorse projections of ethane. The structure on the left is staggered and the structure on the right is eclipsed. These are the simplest sawhorse projections because they have only two carbons and all of the groups on the front and back carbons are identical. Did you know? In petroleum geology and chemistry, cracking is the process whereby complex organic molecules such as heavy hydrocarbons are broken down into simpler molecules, such as light hydrocarbons, by the breaking of carbon-carbon bonds in the precursors. The rate of cracking and the end products are strongly dependent on the temperature and presence of catalysts. Cracking is the breakdown of a large alkane into smaller, more useful alkanes and alkenes. Simply put, hydrocarbon cracking in this process of breaking long-chain hydrocarbons into short ones. Summary. Let us summarize what we have learned. Hydrocarbons are the compound of carbon and hydrogen only. Hydrocarbons are mainly obtained from coal and petroleum, which are the major source of energy. Hydrocarbons are classified as open-chain saturated and unsaturated cyclic and aromatic according to their structure. The important reactions of alkanes are free radical substitution, combustion, oxidation, and aromatization. Alkanes show conformational isomerism due to free rotation along the C-C sigma bonds. out of staggered and eclipsed conformations of ethane. Staggered conformation is more stable as hydrogen atoms are farthest apart. Introduction.
Don't scrub, Ankush. Let me study.
What are you studying?
I'm doing my homework of chemistry.
You are doing wrong.
What are you doing?
Now this is correct.
No, this is double bond and this is an alkene.
Teacher has taught us about single bond and alkanes, but she did not teach alkenes. What are they?
Alkenes are unsaturated hydrocarbons and so are alkynes. Come, I'll tell you in detail about alkenes and alkynes.
Objectives. At the end of this lesson, you will be able to explain alkenes and alkynes, name alkenes and alkynes according to IUPAC system of nomenclature, recognize and write structures of isomers of alkenes and alkynes, learn methods to prepare alkenes and alkynes, write the physical and chemical properties of alkenes and alkynes. Alkenes. Alkenes are class of hydrocarbons which contain only carbon and hydrogen. Two other terms which describe alkenes are unsaturated and olefins. Unsaturated hydrocarbons contain either double or triple bonds. Since the compound is unsaturated with respect to hydrogen atoms, the extra electrons are shared between two carbon atoms, forming double bonds in alkenes. Alkenes are also called olefins because they form oily liquids on reaction with chlorine gas. These are the compounds of ethene or ethylene and pentene. Structure of double bond. The chemical bonding in alkenes can be illustrated by reference to the simplest alkene, ethene. Ethene is not a very complicated molecule. It contains two carbon atoms that are double bonded to each other, with each of these atoms also bonded to two hydrogen atoms. This forms a total of 3 bonds to each carbon atom, giving them an sp2 hybridization. Since the carbon atom is forming 3 sigma bonds instead of the 4 that it can, it only needs to hybridize 3 of its outer orbitals instead of 4. It does this by using the 2s electron and 2 of the 2p electrons, leaving the other unchanged. This new orbital is called an sp2 hybrid because that's exactly what it is. It is made from one s orbital and 2 p orbitals. When atoms are an sp2 hybrid, they have a trigonal planar structure. These structures are very similar to a peace sign. There is a central atom with 3 atoms around it, all on one plane. Trigonal planar molecules have an ideal bond angle of 120 degree on each side. The HCH bond angle is 117 degree, which is very close to the ideal 120 degree of a carbon with sp2 hybridization. The other two angles, HCC, are both 121.5 degrees. Nomenclature of alkenes. Step 1. Find the longest continuous chain that includes the double bond. Step 2. Use the ending end to indicate the presence of carbon-carbon. Step 3. Number of the chain so that the first carbon of the carbon-carbon reached has the lowest possible number. Step 4. Name and number substituents in the same fashion as in alkanes. This is 1-butene and these are 2-methyl-2-butene and 3-methyl-1-butene. Step 5. The alkene functional group takes precedence over alkyl and halide functional groups. Step 6. The alcohol functional group takes precedence over the alkene functional group. 4-bromo-3-methyl-1-butene. Nomenclature of alkenes, Part 2. Step 7. Hydroxyl groups takes precedence over the double bond when the chain is numbered. This compound is 2-methyl-3-butane-1-ol. Step 8. If more than one double bond is present, indicate their position by using the number of the first carbon of each double bond and use the suffix diene for 2 double bonds, triene for 3 double bonds, tetraene for 4 double bonds, etc. For example, 1,4-pentadiene. Step 9. Cycloalkenes are named in a similar way. Number the cycloalkene, so the double bond carbons get numbers 1 and 2, and the first substituent is the lowest possible number. If there is a substituent on one of the double bond carbon, it gets number 1. 6-ethyl-1-methyl cyclohexene. Look at this compound. It is named as 1,5-dimethyl cyclopentene and not 2,3-dimethyl cyclopentene. Isomerism. Structural isomerism. All the alkenes with 4 or more carbon atoms in them show structural isomerism. This means that there are 2 or more different structural formulae that you can draw for each molecular formula. For example, with C4H8, it isn't too difficult to come up with these 3 structural isomers. There is, however, another isomer. But-2-ene also exhibits geometric isomerism. Geometric cis-trans isomerism. The carbon-carbon double bond doesn't allow any rotation about it. That means that it is possible to have the CH3 groups on either end of the molecule locked either on one side of the molecule or opposite each other. These are called cis-but-2-ene, where the groups are on the same side, or trans-but-2-ene, where they are on the opposite sides. Cis-but-2-ene is also known as Z-but-2-ene. Trans-but-2-ene is also known as E-but-2-ene. Preparation of alkenes, Part 1. Alkenes are generally prepared through beta elimination reactions, in which 2 atoms on adjacent carbon atoms are removed, resulting in the formation of a double bond. Alkenes are usually prepared from either alcohols or haloalkanes, alkyl halides, by the dehydration of alcohols. In dehydration reactions, a molecule of water is eliminated from an alcohol molecule by heating the alcohol in the presence of a strong mineral acid. A double bond forms between the adjacent carbon atoms that lost the hydrogen ion and hydroxide group. From haloalkanes or alkyl halides. Alkenes can be obtained from haloalkanes, alkyl halides. These haloalkanes are usually bromo and iodo and less commonly chloro derivatives. Preparation of alkenes, Part 2. By dehydrogenation of haloalkanes. Haloalkanes on heating with alcoholic potash loses one molecule of hydrogen halide to give alkene. Bromoethane gives ethane. Dehalogenation. Vicinal dihalides, which are alkane molecules that contain 2 halogen atoms on adjacent carbon atoms, can form alkenes upon reaction with zinc. From alkynes. Alkenes can be easily obtained by hydrogenation of alkynes. An alkyne on controlled hydrogenation with hydrogen in the presence of Ni or Pd at 200 degrees centigrade gives corresponding alkene. Ethine gives ethene on hydrogenation. Physical properties of alkenes. Physical state. Alkenes can exist in all the 3 physical states, gases, liquids and solids at room temperature. At room temperature, lower alkenes, first 3 alkenes, are colorless gases, while next 14 members, those comprised of 5 to 15 carbon atoms, are colorless liquids. The higher alkenes are colorless solids. Except ethene, all other alkenes are colorless and odorless. Ethene has a faint sweet smell. Because of non-polar nature of alkenes, they are insoluble in water, but soluble in non-polar solvents like benzene, carbon tetrachloride and petroleum ether, etc. Density. Alkenes have densities less than 1 gram per milliliter and are therefore less dense than water, hence form separate layer above water. As the molecular mass of alkenes increases, density increases. Boiling points of alkenes. In liquid state, molecules are packed closely together with weak intermolecular force of attraction, hence can be moved randomly in system. When we supply heat to the liquid, temperature of system increases, which contributes in the increment in kinetic energy of molecules. Hence, the molecule motion increases and the forces of attraction between the molecules decreases at high temperature. Just like boiling point, melting points of alkenes also increase with an increase in the molecular mass. Chemical properties of alkenes Part 1. Alkenes are more reactive than alkanes due to the presence of a double bond. The carbon-carbon double bond consists of a strong bond and a weak p bond. Addition reactions. The p electrons of the carbon-carbon double bond are available to an electrophile, any species seeking electrons. Thus, the addition reactions shown by alkenes are in fact electrophilic addition reactions. Addition of hydrogen. Alkenes add hydrogen in the presence of platinum or nickel catalyst to form alkanes. The reaction termed as hydrogenation is an exothermic reaction. Addition of halogens. Alkenes react with halogens to form dihaloalkanes. The order of reactivity is chlorine is greater than bromine is greater than iodine. Simply mixing together the two reactants, usually in an inert solvent like carbon tetrachloride, best carries out the reaction. Addition of halogen acids. Alkenes with concentrated aqueous solution of halogen acids give haloalkanes. The order of reactivity is Hi is greater than HBr is greater than HCl. In asymmetrical alkenes, the addition of a halogen acid takes place in a manner whereby the halogen atom, the negative part of the molecule to be added, adds to the carbon atom, which has lesser number of hydrogen atoms on it. For example, in the case of propene, the product obtained is 2-iodopropane and not 1-iodopropane. This rule of addition of halogen acids to an asymmetrical alkene is known as Markovnikov's rule. Chemical properties of alkenes Part 2. Addition of sulfuric acid. In accordance to Markovnikov's rule, alkenes readily add concentrated sulfuric acid to form alkyl hydrogen sulfates. For example, ethene react with ethane sulfuric acid to give ethyl hydrogen sulfate. Addition of water, hydration of alkenes. Water molecules add to an alkene molecule across the double bond in the presence of dilute acid and a catalyst. For example, ethane gives ethanol when a mixture of ethene and steam is passed over phosphoric acid and silica under a pressure 65 atmosphere and at 300 degrees centigrade. Addition of ozone. Ozonides are formed when alkenes add a molecule of ozone across the double bond. For example, ethene gives ethene ozonide. Polymerization. Addition polymerization is a process by which a large number of molecules of the same species join together without the elimination of simple molecules like HX, H2O, etc. to form a giant molecule called a polymer. Alkenes undergo addition polymerization when heated under pressure in the presence of suitable catalysts. When ethene is heated to 1000 degrees centigrade under 1000 atmospheric pressure in presence of oxygen, we get polyethene. Alkynes. Alkynes are hydrocarbons which contain a triple carbon-carbon bond. As with alkenes, the simplest member of the series is 2-carbon molecule. The triple bond is indicated by changing the ending of the name to -ine, in the same manner as the double bonds in alkenes are indicated by the ending -ene. Alkynes, like alkenes, are unsaturated hydrocarbons with the general formula CnH2n-2. They are very unstable and quite reactive. For example, ethyne, the simplest alkyne, which is more commonly known by its common name acetylene, is a gas often used as a fuel for cutting and welding torches because it burns with a very hot flame. Naming alkynes. In IUPAC system, the alkynes are named as derivatives of alkanes. The suffix -ane is replaced with -ine in the alkane name. For example, the given compound has 3 carbon atoms and hence the root name is propane. If the suffix ane is replaced with ine, we will get the IUPAC name of the compound as propyne. If there is a substitute in the chain, the longest chain is selected in such a way that the chain contains the triple bond. Similarly, the chain is numbered in such a way that the carbon containing the triple bond gets the least number. For example, the given compound contains 5 carbon atoms in the longest chain, hence it is named as pentyne. It is named from the right to left so that the carbon containing triple bond gets the number 1. There is one substitute methyl group at third carbon atom, hence the name of the compound is 3-methyl-1-pentyne. Structures of alkynes. In the structure of alkynes, the carbon atom undergoes sp hybridization. The outermost electronic configuration of carbon is 2s2 2p2. In the excited state, one electron from 2s orbital is excited to 2p. Hence, the electronic configuration in the excited state is 2s1, 2px1, 2py1, 2pz1. Here, the carbon undergoes sp hybridization to give 2 sp hybridized orbitals with linear shape and with bond angle as 180 degrees. One of the sp hybridized orbitals is connected with other carbon and other is connected with hydrogen. Hence, the structure of acetylene molecule is linear. Isomerism. Chain isomers. Compounds having same molecular formula with different in carbon chain pattern like linear or branch are called chain isomers. 1-pentyne is chain isomer of 3-methylbutene. Position isomers. Compounds having same molecular formula with difference in position of the functional group are called as position isomers. 1-butene and 2-butene are position isomers. Functional group isomers. Compounds having same molecular formula with difference in nature of functional group are called as functional group isomers. Alkynes are functional group isomers for cycloalkenes. For example, pentyne and cyclopentene are functional group isomers. Geometrical isomers. The bond between carbon atoms in alkyne is rigid and cannot be rotated. Hence, there should be possibility of geometrical isomers. But the orientation of atoms cannot be determined. Hence, there is no possibility of geometrical isomerism in alkynes. Preparation of alkynes. The preparations of alkynes are very similar to those of the alkenes. The main preparative reactions involve the elimination of groups or ions from molecules, resulting in the formation of pi bonds. Dehydrohalogenation. The loss of an hydrogen atom and a halogen atom from adjacent alkane carbon atom leads to the formation of an alkene. The loss of the additional hydrogen and halogen atoms from the double bonded carbon atoms leads to the alkyne formation. The halogen atoms may be located on the same carbon, a geminal dihalide, or on adjacent carbons, a vicinal dihalide. During the second dehydrohalogenation step, certain conditions are necessary, namely high temperatures and an extremely strong basic solution. Dehalogenation. Vicinal tetrahaloalkanes can be dehalogenated with zinc metal in an organometallic reaction to form alkynes. Substitution. Larger alkynes can be generated by reacting an alkyl halide with an acetylide ion, which is generated from a shorter alkyne. Ethyne acetylene preparation. Ethyne, which is commonly called acetylene, is the simplest alkyne. Historically, it was prepared by reacting calcium carbide with water. Today, ethyne is normally prepared by the pyrolysis of methane. In this procedure, a stream of methane gas is briefly heated to 1500 degrees centigrade in an airless chamber. Air must be excluded from the reaction or oxidation combustion will occur. Physical properties of alkynes. The physical properties of alkynes are very similar to those of the alkenes. Alkynes are generally nonpolar molecules with little solubility in polar solvents, such as water. Solubility in nonpolar solvents, such as ether and acetone, is extensive. Like the alkanes and alkenes, alkynes of 4 or fewer carbon atoms tend to be gases. Substituted alkynes have small dipole moments due to differences in electronegativity between the triple bonded carbon atoms, which are sp hybridized, and the single bonded carbon atoms, which are sp3 hybridized. The sp hybridized carbon atom, which possesses more s character than the sp3 hybridized carbon atom, is more electronegative in character. The resulting asymmetrical electron distribution in the bond between such carbon atoms results in the generation of a dipole moment. Chemical properties of alkynes. Combustion. Alkynes burns in air or oxygen with smoky flame. Addition of hydrogen. An alkyne reacts with hydrogen in the presence of catalyst, Pt or Ni, at 250 degrees centigrade, first forming alkenes and finally alkanes. Addition of halogens. Alkynes react with halogens, Cl2 or Br2, in the dark, forming dihaloalkenes, first and finally tetrahaloalkanes. The reaction gets accelerated in the presence of light or halogen carriers. Addition of water. In the presence of sulfuric acid, 42% and 1% mercuric sulfate at 60 degrees centigrade, alkynes add on one water molecule to give aldehydes or ketones. For example, ethine gives ethanol and propyne gives acetone. Polymerization. On heating, alkynes undergo polymerization in the presence of catalyst. The nature of products depends upon the conditions. For example, when ethyne acetylene is passed through a hot copper tube, it polymerizes to benzene. When passed through a solution of cuprous chloride in ammonium chloride, ethyne undergoes linear polymerization. Did you know? Markovnikov's rule was formulated by the Russian chemist Vladimir Vasilievich Markovnikov in 1870. Mechanisms that avoid the carbocation intermediate may react through other mechanisms that are regioselective against what Markovnikov's rule predicts, such as free radical addition. Such reactions are said to be anti-Markovnikov, since the halogen adds to the less substituted carbon, exactly the opposite of Markovnikov reaction. Again, like the positive charge, the radical is most stable when in the more substituted position. Summary. Let us summarize what we have learnt. Alkenes are class of hydrocarbons which contain only carbon and hydrogen. Two other terms which describe alkenes are unsaturated and olefins. Unsaturated hydrocarbons contain either double or triple bonds. Alkynes, like alkenes, are unsaturated hydrocarbons with the general formula CnH2n-2. They are very unstable and quite reactive. Alkenes and alkynes undergo addition reactions, which are mainly electrophilic additions. Alkenes exhibit geometrical cis-trans isomerism due to restricted rotation around the carbon-carbon double bond.
Introduction. Today's morning is very good. Yes, Dad, it is a sunny day. So, how is your study going? The study is going very good, Dad. Excellent, Aryan. Dad, I want to ask you something. Yes, dear. Dad, all these vehicles such as cars, trucks, etc. run on fuel. Yes. Does the space shuttle also run on the same fuel? My son, a special type of fuel is used in space shuttle. What kind of special fuel, Dad? They use hydrogen in the external tank to lift off the space shuttle. Would you like to learn more of it? Yes, Dad. In this lesson, you will learn hydrogen and its compound. Objectives. At the end of this lesson, you will be able to locate the hydrogen in the periodic table and define the isotopes of hydrogen. Explain the preparation of dihydrogen, physical and chemical properties of dihydrogen. Explain hydrides. Position of hydrogen in the periodic table. Hydrogen is the first element of the periodic table with atomic number 1. As it has only one electron, so its electronic configuration is 1s1. Because of the dual behavior of hydrogen, it is quite difficult to find a proper place in periodic table as it has resemblance with alkali metals and with the halogens. Like alkali metals, it has only one electron in its valence shell. Like halogens, hydrogen is short only by one electron to complete the inert gas configuration. Dihydrogen, H2. Occurrence. Dihydrogen is the most spontaneous element in the universe. It has about 70% of the universe's total mass. Jupiter and Saturn mostly consist of hydrogen. Half of the mass of the Sun and some other stars made up of hydrogen. In the combined form, it forms 15.4% of the Earth's crust and oceans. Earth does not have enough gravitational pull to retain the light hydrogen molecule, so it is not found in our atmosphere. Isotopes of hydrogen. Hydrogen has three isotopes. Protium. Its atomic number is 1 and mass number is also 1. It has one proton but no neutron in its nucleus and one electron in its 1s orbital. It is represented by symbol H. Its abundance is 99.985%. Deuterium. Its atomic number is 1 and is 2. It has one proton and one neutron in its nucleus and one electron in its 1s orbital. It is represented by symbol D. Its abundance is 0.0156%. Tritium. Its nucleus has one proton and two neutrons and there is one electron in its 1s orbital. It is an extremely rare isotope. Out of 10 to the power 18 molecules of ordinary hydrogen, there is just one molecule of tritium. This isotope of hydrogen is radioactive in nature and emits low-energy beta particles. Its abundance is 10 raised to the power minus 15%. Preparation of dihydrogen, H2. Laboratory preparation of dihydrogen. In the laboratory, hydrogen is generally prepared by the action of dilute mineral acids on metals such as granulated zinc. Few pieces of granulated zinc are placed in valve bottle which is fitted with a thistle funnel and a delivery tube. Dilute sulfuric acid is poured through thistle funnel. The acid reacts with zinc, evolving hydrogen, which is collected in jar by downward displacement of water. Pure zinc is not used as it is non-porous and therefore, after some time, the reaction slows down. Hence, granulated zinc is used that is impure and it increases the rate of reaction. Commercial production of dihydrogen. Electrolysis of water. It involves the electrolysis of acidified or alkaline water. We use dilute H2SO4 to make water acidified. Dilute sulfuric acid is enough to make water act as an electrolyte. When anode and cathode are connected to a battery, it produces a small amount of current of the order of few milliamperes and bubbles start appearing in the two arms of the voltmeter. The anode collects oxygen and the cathode arm collects hydrogen gas. The reactions taking place are dissociation of H2SO4. H2SO4 gives 2H plus SO4 2 minus. Dissociation of H2O. H2O gives H plus OH minus. Reaction at cathode. H plus electron gives H. H plus H gives H2. Reaction at anode. OH minus gives OH plus electron. 4OH gives H2O plus O2. Overall reaction: 2H2O gives 2H2 plus O2. At the anode, OH- ions are released in preference to SO4 2- ions. This is because it is easier for an OH- ion to give up an electron quickly than for the SO4 2- ion to do so. Since the sulfuric acid itself does not participate in the chemical reaction that is taking place, it can be called as a catalyst of the reaction. Commercial production of dihydrogen. Dihydrogen can be prepared by the action of steam with red-hot coke as given below. The water gas formed is also called synthesis gas or syngas. Then water gas is mixed with steam and is passed over heated Fe2O3 and Cr2O3 at 770 Kelvin. Then CO is oxidized to CO2. Gaseous mixture of CO2 and H2 is then bubbled into cold water under pressure, when CO2 dissolves, leaving behind dihydrogen gas which escapes out. This reaction is called water-gas shift reaction. Properties of dihydrogen. Physical properties. It is colorless, odorless, tasteless gas. It is lighter than air and collected by downward displacement of water because it is insoluble in water. It is highly combustible. It is the lightest of all elements. Chemical properties of dihydrogen. Reaction with halogens. The reactivity of halogens with hydrogen is fluorine greater than chlorine, greater than bromine, greater than iodine. Hydrogen reacts with halogens to give hydrogen halides. Reaction with dioxygen. Hydrogen reacts with dioxygen to give water. Chemical properties of dihydrogen. Reaction with dinitrogen. Hydrogen reacts with dinitrogen to give ammonia. Reaction with metals. Hydrogen reacts with metals to form hydrides, where M is an alkali metal. For example, 2Na plus H2 on temperature 525 Kelvin gives 2NaH. Chemical properties of dihydrogen. Reaction with metal ions and metal oxides. Hydrogen reacts with metal ions and metal oxides to give corresponding metal. For example, reactions with organic compounds. When hydrogen is passed through edible vegetable oils at about 473 Kelvin in presence of finely divided nickel as a catalyst, they undergo hardening and change into edible fat. Uses of dihydrogen. It is used in synthesis of ammonia. Nitrogen and hydrogen passed to heater, where these are heated up to a certain temperature. After that, they are compressed and then passed to heater, where the reaction takes place. After that, the mixture is passed to waste heat boiler, from which ammonia is cooled and then stored, and nitrogen and hydrogen are recycled. It is used in the manufacture of vanaspati ghee. It is used as a rocket fuel in space research. It is used in fuel cells for generating electrical energy. Hydrides. Hydrides are referred to binary compounds that hydrogen forms with other elements of the periodic table except noble gases. Hydrides can be categorized as ionic or saline hydrides. The ionic hydride form between hydrogen and the most active metals, especially with the alkali and alkaline earth metals of group 1 and 2 elements. In this group, the hydrogen acts as the hydride ion. They bond with more electropositive metal atoms. Electrolysis of solution of saline hydride in molten alkali halide produces H2 at anode. The reaction is given as: alkali metal hydrides are also used for the removal of last traces of water from organic compounds. Covalent or molecular hydrides. Hydrogen form molecular compounds with p-block elements. Common examples of such hydrides are CH4, NH3, H2O, HF, etc. The stability of these hydrides decreases down the group. For example, in a period, the stability increases with increasing electronegativity. For example, covalent or molecular hydrides. Molecular hydrides are classified as electron-rich molecular hydride. These hydrides have one or more lone pairs of electrons around the central more electronegative element. For example, water has 2 lone pairs. Electron-precise molecular hydride. These hydrides have required number of electrons for Lewis structure. A common example of electron-precise molecular hydride is methane. Electron-deficient molecular hydride. These hydrides have lesser number of electrons than that required for Lewis structure. A common example of such molecular hydride is diborate. Metallic or non-stoichiometric or interstitial hydrides. These hydrides are generally formed by the transition metal of group 3, 4, 5 of D- block, Cr metal of group 6, F- block metals. The elements of group 7, 8, 9 of D- block do not form hydrides at all. This inability of metal of group 7, 8, 9 of periodic table to form hydrides is referred to as hydride gap of D- block. In these compounds, H atoms occupy interstitial positions in the metal lattices. For example, SCH2, LaH2.87. Did you know? Boeing unveils new hydrogen-powered aircraft. Boeing has been working to make new aircraft more environmentally friendly. Boeing and others have been developing new aircraft that make use of alternative energy. Further tests with the aircraft will help Boeing understand the best use for the fuel cell and the other technologies it has chosen for the plane.
Summary.
Let us summarize what we have learned. Hydrogen is the first element of the periodic table with atomic number 1. 3 isotopes of hydrogen are protium, deuterium and tritium. In laboratory, dihydrogen is prepared by the treatment of zinc granules with dilute sulfuric acid. Hydrogen is colorless, odorless, tasteless gas and highly combustible gas. Hydrogen reacts with halogens to give hydrogen halides. Hydrogen reacts with dioxygen to give water. Hydrogen reacts with dinitrogen to give ammonia. Hydrogen reacts with metals to form hydrides. Hydrogen reacts with metal ions and metal oxides to give corresponding metal. Hydrides can be categorized as ionic, covalent and metallic hydrides. Introduction. Hey kids, today we will learn water, hydrogen peroxide and heavy water. Water is a chemical substance and its chemical formula is H2O. It is a colorless and transparent liquid. It contains 1 oxygen atom and 2 hydrogen atom. Hydrogen peroxide is a combination of hydrogen and oxygen. Its chemical formula is H2O2. Heavy water is a deuterium oxide. It is another form of water which contains hydrogen deuterium isotope. So, Throughout this module, we will learn water, hydrogen peroxide, and heavy objectives. At the end of this lesson, you will be able to discuss physical and chemical properties of water, discuss structure of ice and water, distinguish hard and soft water, explain the methods of preparation of hydrogen peroxide and discuss its physical and chemical properties, define heavy water and discuss dihydrogen as a fuel. Water. Water is most common, abundant and easily obtainable of all chemical compounds. It is a crucial compound for man's survival. It can exist in solid, liquid or gaseous forms. It is the universal solvent. 70% of our body contains water. 75% of Earth consists of water. Physical properties of water. It is colorless, odorless and tasteless liquid. The blue or bluish-green tint of water is due to its depth. Water's freezing point is 0 degrees Celsius and its boiling point is 100 degrees Celsius. When frozen, it expands by 1/9 of its original volume. The boiling point of water depends upon the pressure on its surface. The higher the pressure, the higher the boiling point. Structure of water. A water molecule consists of 2 hydrogen atoms and 1 oxygen atom. It has high polarity. The 3 atoms make an angle. The HOH angle is approximately 104.5 degrees. The center of each hydrogen atom is approximately 95.7 picometer from the center of the oxygen atom. As oxygen is more electronegative than hydrogen, the hydrogen atoms end up with a partial positive charge and the oxygen atom with a partial negative charge. This separation of charge produces a net dipole moment on the molecule. The solid form of water is ice and the density of ice is less than that of water. Structure of ice. Ice has 3-dimensional network in which each oxygen atom is surrounded tetrahedrally by 4 other oxygen atoms at a distance of 276 picometer. 3-dimensional structure of ice has got an open space, that is why it has less density and floats over water. Chemical properties of water. Amphoteric nature. The ability of some chemicals act either as an acid or a base is called amphoterism. If a base like NH3 is present, water can act as an acid and react by donating a proton to that base. If an acid like H2S is present, water can act as base and react by accepting a proton from that acid. The self-ionization of water is another example of water being able to react either as an acid or a base. Redox reactions involving water. Dihydrogen can be produced by the reduction of water as given. Chemical properties of water. Hydrolysis reaction. The reaction of compounds with water to form new compounds is called hydrolysis. For example, dinitrogen pentoxide reacts with water to form nitric acid. Hydrates formation. Water form hydrates with metal salts. There are 3 main types. Coordinated complex compounds. For example, nickel 2 nitrate hexahydrate. Coordinate bond is formed between O of H2O with metal ion. H bonded. For example, copper sulfate pentahydrate. Interstitial hydrates. Water is present in some compound as interstitial water. For example, BaCl. Hard and soft water. Hard water. The water which contains dissolved salts of Ca2+, Mg2+, and Fe2+ is called hard water. It does not form enough lather with soap. Soft water. It does not contain dissolved salt of calcium, magnesium, iron. It forms enough lather with soap. It is free from bicarbonates, sulfates, chlorides of Ca2+ and Mg2+. Fatty acids. Those acids which contain higher alkyl chain are called fatty acids. For example, C15H31COOH, C17H35COOH. Hard water forms precipitate on reacting with soap. Reaction of hard water with soap. Hard and soft water. Water hardness is of two types. Temporary hardness. It is caused by the presence of bicarbonate of calcium and magnesium that are, and it can be removed by boiling. Soluble bicarbonates change to carbonates which are insoluble and get precipitated. Clark's method. When calculated quantity of lime is put in, it causes precipitation of calcium carbonate. Permanent hardness. It is the hardness caused by the presence of chlorides and sulfates of Ca2+, Mg2+, and Fe2+. It can be removed by treatment with washing soda or sodium carbonate. Sodium carbonates converts calcium and magnesium salts to insoluble carbonates which can be filtered off. Calgon's method. It is sodium hexametaphosphate. The complex anion keeps the Mg2+ and Ca2+ ions in solution. Ion exchange method. Zeolite or hydrated sodium aluminium silicate is called permuted. NaAlSiO4 3H2O is used to remove Ca2+ and Mg2+. The zeolite can be regenerated by treatment with NaCl solution. Synthetic resins method. Synthetic resins method. Hard water can be softened by using synthetic cation exchangers. They are more efficient than zeolite and permuted. These cation exchangers are large organic molecules containing sulfonic acid, RSO3H group. The ion exchange resin is first changed to the sodium form by treatment with NaCl solution and then used for softening of water. The resin can be regenerated for further use by treatment with NaCl solution. Hydrogen peroxide, H2O2. Preparation. Hydrogen peroxide can be prepared by the action of sulfuric acid or phosphoric acid on hydrated barium peroxide. Anhydrous barium peroxide does not react readily with sulfuric acid because a coating of insoluble barium sulfate is formed on its surface which stops further action of the acid. Therefore, hydrated barium peroxide, BaO2,8H2O must be used. Industrially, it is prepared by the auto-oxidization of 2-alkylyl anthraquinols. When 2-ethyl anthraquinol is oxidized in the presence of hydrogen or palladium, it gives hydrogen peroxide. Physical properties. Hydrogen peroxide is a clear and colorless liquid. It has a slightly pungent odor. Hydrogen peroxide is a versatile and environmentally friendly chemical with a wide variety of applications. Structure. Hydrogen peroxide has a non-planar structure. In gas phase, dihedral angle is 111.5 degree. In solid phase at 110 Kelvin, dihedral angle is 90.2 degree. Chemical properties. Hydrogen peroxide can act as oxidizing as well as reducing agent. Oxidizing action in acidic medium. Reducing action in acidic medium. Oxidizing action in basic medium. Reducing action in basic medium. Storage. Hydrogen peroxide should be stored in roofed, fireproof rooms where it can be kept cool and protected from direct sunlight. It is very important that hydrogen peroxide should be protected against all types of contamination. With proper storage in the original containers or in tank installations, the solutions can be stored for long periods without noticeable losses in active oxygen. Uses. It is used as an antiseptic and for mouthwash. It is used in chemicals manufacturing food, water and wastewater treatment. It is also used in biological sewage treatment in cases where there is a lack of oxygen due to overload of biological treatment plants. It is used in oxidation of formaldehydes, phenols, organic chlorine compounds, etc. Heavy water, D2O. Heavy water is the oxide of heavy hydrogen and is also called deuterium oxide. The credit of discovery of heavy water goes to Urey, who first proved that 6,000 parts of ordinary water contains about 1 part of heavy water. Demonstration of heavy water. Firstly, take 2 beakers filled with water. Drop an ice cube which is blue in color in the first beaker and see that ice floats on water. In another beaker, drop another ice cube which is red in color of heavy water D2O. You will see that the ice cube sinks in the water. This is due to the fact that deuterium is heavier isotope than hydrogen and it changes physical and chemical properties of water. Dihydrogen as a fuel. Hydrogen can be used as a source of energy. It involves the production of large quantities of hydrogen electrically and its storage in liquid form in vacuum-insulated cryogenic tanks and used in space programs. Hydrogen can be a future source of energy. Advantage of hydrogen as an automobile fuel. It produces greater energy per unit mass of fuel due to high calorific value. It is pollution-free. Combustion products of hydrogen in presence of air will be H2O and traces of oxides of nitrogen. Internal combustion engines can be easily modified for use of hydrogen as a fuel. 5-point fuel cells generation of electric power with efficiency 70 to 85% have successfully operated commercially in space vehicles. Did you know? Hydrogen peroxide can be used to induce vomiting when a dog has ingested poison. Gold nanoparticles can be used to produce hydrogen fuel.
Summary.
Let us summarize what we have learned. Water is most common, abundant, and easily obtainable of all chemical compounds. The HOH angle is approximately 104.5 degrees. The center of each hydrogen atom is approximately 95.7 picometer from the center of the oxygen atom. Water has the ability to act either as an acid or a base is called amphoterism. The water which contains dissolved salts of Ca2+, Mg2+, and Fe2+ is called hard water. The water which does not contain dissolved salts of calcium, magnesium, iron, etc. is called soft water. It forms enough lather with soap. It is free from bicarbonates, sulfates, chlorides of Ca2+ and Mg2+. Temporary hardness can be removed by boiling and Clark's method. Permanent hardness can be removed by treatment with washing soda, Calgon's method, ion exchange method, and synthetic resins method. Hydrogen peroxide can be prepared by the action of sulfuric acid or phosphoric acid on hydrated barium peroxide. Hydrogen peroxide has a non-planar structure. Heavy water is the oxide of heavy hydrogen and is also called deuterium oxide.
परिचय। आज भौतिकी के शिक्षक प्रयोगशाला में छात्रों के सामने हम एक प्रयोग करने जा रहे हैं। उन्होंने एक छोटा गुब्बारा लिया और इसे निर्वात जार में रख दिया। फिर उन्होंने वैक्यूम पंप का स्विच चालू कर दिया। अचानक गुब्बारा फैलने लगा। उनके द्वारा पंप का स्विच बंद कर देने के कुछ देर बाद गुब्बारा अपनी मूल अवस्था में आ गया। एक छात्र ने कौतूहलवश पूछा, श्रीमान जी, क्या आप कृपया बताएंगे कि यह प्रक्रम कैसे कार्य करता है? हाँ, निश्चित रूप से वरुण। ये अणुगति सिद्धांत का एक उदाहरण है। जब निर्वात को ऑन किया जाता है तो गुब्बारे पर लगने वाला दाब घट जाता है और निर्वात जार पूरा भर जाने तक गुब्बारा फैलता है। और जब वायु वापस जार में आती है तो दाब पुनः लगता है और गुब्बारा अपने मूल आयतन में वापस आ जाता है। ये दाब तथा आयतन के बीच एक अप्रत्यक्ष संबंध दिखाता है। तो छात्रों, हम आज अणुगति सिद्धांत के बारे में और अधिक जानकारी प्राप्त करेंगे। उद्देश्य। इस पाठ के अंत में आप निम्न करने में सक्षम हो जाएंगे: अणुगति सिद्धांत को परिभाषित करना, द्रव्य की आणविक प्रकृति की व्याख्या करना, गैसों के व्यवहार को समझना, बॉयल के नियम तथा चार्ल्स के नियम को परिभाषित करना, आदर्श गैस के अणुगति सिद्धांत को जानना, आदर्श गैस के ताप की गणना करना, ताप की अणुगतिक व्याख्या करना, मैक्सवेल बंटन फलन को समझना, ऊर्जा समविभाजन के नियम को परिभाषित करना, विशिष्ट ऊष्माधारिता की गणना करना, माध्य मुक्त पथ तथा ब्राउनी गति को परिभाषित करना। परिभाषा। अणुगति सिद्धांत 19वीं शताब्दी में मैक्सवेल, बोल्ट्जमान तथा अन्य द्वारा विकसित किया गया। अणुगति सिद्धांत इस विचार के आधार पर गैसों के व्यवहार की व्याख्या करता है कि गैसें तेजी से गति करने वाले परमाणुओं या अणुओं से बनी होती हैं। यह संभव है कि अंतर परमाणुविक बल, जो लघु परास के बल होते हैं, और ठोसों तथा द्रवों के लिए महत्वपूर्ण होते हैं, वे गैसों के लिए उपेक्षित किए जा सकते हैं। द्रव्य की आणविक प्रकृति। किसी गैस में सभी अणु सदृश होते हैं, लेकिन वे अन्य गैसों के अणुओं से भिन्न होते हैं। किसी गैस के अणु आदर्श प्रत्यास्थ गोलों की तरह व्यवहार करते हैं और अणुओं के बीच की दूरियों की तुलना में बहुत छोटे आकार के होते हैं। सभी अणु सदैव यादृच्छिक गति करते हैं और सभी दिशाओं में उनके वेग 0 से लेकर अनंत तक होते हैं। अपनी गतियों के दौरान अणु एक दूसरे से तथा पात्र की दीवारों से भी संघट्ट करते हैं। ये सभी संघट्ट आदर्श रूप से प्रत्यास्थ होते हैं। संघट्ट के दौरान को छोड़कर अणु एक दूसरे पर कोई बल नहीं लगाते। दो संघट्टों के बीच अणु सदैव एक सीधी रेखा में गमन करते हैं और दो क्रमिक संघट्टों के बीच चली गई दूरी माध्य मुक्त पथ कहलाती है। गैसों का व्यवहार। सभी गैसें गर्म करने पर फैलती हैं। जहां तक आयतन में परिवर्तन का संबंध है, ठोसों तथा द्रवों पर दाब का प्रभाव नगण्य होता है। लेकिन गैसों को आसानी से संपीड़ित किया जा सकता है। वे स्थिर ताप पर भी आयतन में प्रसारित होती हैं, यदि दाब को गिरने दिया जाए। इसलिए गैस का आयतन न केवल ताप पर बल्कि इस पर लगने वाले दाब पर भी निर्भर करता है। बॉयल का नियम। बॉयल के नियम के अनुसार ताप नियतांक रखने पर गैस के किसी दिए गए द्रव्यमान का दाब उसके आयतन के व्युत्क्रमानुपाती होता है। पीवी बराबर स्थिरांक, जहां पी दाब है और वी आयतन है। यह इसका अनुसरण करता है कि यदि गैस का आयतन घटाकर आधा कर दिया जाए तो इसका दाब 2 गुना हो जाएगा। नियतांक ताप पर गैस की ऊर्जा का नियतांक मान होता है और जब तक ताप नियतांक बना रहता है तब तक गैस के प्रसार या संकुचन के साथ ये ऊर्जा बढ़ती या घटती नहीं है। बॉयल के नियम का पूर्णतः पालन करने वाली गैस आदर्श गैस कहलाती है। बॉयल के नियम को इस तरह से कहा जा सकता है कि नियतांक ताप पर गैस का घनत्व इसके दाब से संगत रूप में बढ़ता है। P बटे रो नियतांक। चार्ल्स का नियम। चार्ल्स के नियम के अनुसार किसी गैस का आयतन प्रत्येक 1 डिग्री सेल्सियस ताप पर परिवर्तन के लिए 0 डिग्री सेल्सियस पर इसके आयतन के गामा यानी P परिवर्तित होता है, यदि दाब स्थिर रखा गया हो। V बराबर V नॉट गुणे 1 प्लस गामा P थीटा, जहां V थीटा डिग्री सेल्सियस पर आयतन है तथा V नॉट 0 डिग्री सेल्सियस पर आयतन है। उपरोक्त संबंध को निम्न प्रकार से लिखा जा सकता है। V बराबर V नॉट गुणे 1 प्लस थीटा बटे 273। समीकरण के अनुसार आयतन तथा ताप के बीच ग्राफ एक सीधी रेखा होता है। ताप के पूरे परास में आदर्श गैस इस समीकरण का पालन करती है। वास्तविक गैसें केवल उच्च ताप पर ही इस समीकरण का पालन करती हैं। तापमान घटाए जाने पर ये समीकरण से विचलित होने लगती हैं। आदर्श गैस का अणुगति सिद्धांत। गैस में बड़ी संख्या में एक जैसे अणु होते हैं जो छोटे, गोलीय, उदासीन तथा आदर्श प्रत्यास्थ होते हैं और अणु कहलाते हैं। गैस में अणु सभी संभव चालों के साथ सभी संभव दिशाओं में गति करते हैं। अणुओं द्वारा घेरा जाने वाला स्थान गैस के आयतन की अपेक्षा नगण्य होता है। अणुओं के बीच कोई आकर्षण बल नहीं होता। अणुओं के बीच तथा पात्र की दीवारों के साथ संघट्ट पूर्णतया प्रत्यास्थ होते हैं। अणु द्वारा संघट्टों के बीच व्यतीत किए गए समय की तुलना में संघट्ट की अवधि बहुत कम होती है। आणविक गति पर गुरुत्व का कदाचित ही कोई प्रभाव पड़ता है, क्योंकि उनका द्रव्यमान बहुत छोटा होता है और चाल बहुत अधिक रहती है। आदर्श गैस का ताप। पात्र की दीवारों के साथ अणुओं के संघट्ट के कारण गैसें दाब लगाती हैं। आइए m द्रव्यमान वाले अणुओं की n संख्या वाली एक आदर्श गैस पर विचार करें, जो भुजाओं Lx, Ly, Lz वाले एक आयताकार बॉक्स में भरी है। गतिज ऊर्जा प्रति इकाई आयतन निम्न द्वारा व्यक्त है। E बराबर 1/2 रो V RMS वर्ग। गैस का दाब निम्न द्वारा व्यक्त है। P बराबर 2/3 ऑफ E। इसलिए गैस का दाब इसकी गतिज ऊर्जा प्रति इकाई आयतन के 2/3 के बराबर होता है। ताप की अणुगतिक व्याख्या। एक अणु की औसत गतिज ऊर्जा E निम्न द्वारा व्यक्त है। E बराबर EM/n बराबर 3RT/2n बराबर 3kT/2, जहां K वोल्टेजमैन नियतांक है। इसलिए अणु की औसत गतिज ऊर्जा गैस की प्रकृति पर या अणु के द्रव्यमान पर निर्भर नहीं होती। इसका अर्थ है कि समान तापमान पर विभिन्न गैसों की कुल गतिज ऊर्जा समान होती है और प्रति अणु औसत गतिज ऊर्जा समान होती है। यह केवल गैस के निरपेक्ष ताप पर निर्भर करता है। तापमान को गैस के अणुओं की औसत गतिज ऊर्जा की माप के रूप में स्पष्ट किया जा सकता है। उदाहरण। आइए एक आदर्श गैस के अणुगति सिद्धांत का उदाहरण देखें। आदर्श गैस समीकरण PV बराबर RT का उपयोग करके सार्वत्रिक गैस नियतांक के मान की गणना करें। आइए इसका हल देखें कि हमारे पास है V बराबर 22,400 गुणे 10 की घात -6 m घन, T बराबर 273 K, PV बराबर RT, P बराबर HDG। अब हम मानों को रखते हुए R के मान की गणना करते हैं। R बराबर PV/T बराबर 2 कैलोरी मोल की घात -1 K की घात -1, यदि V बराबर 22.4 लीटर। P बराबर 1 वायुमंडल, T बराबर 273 K, R बराबर 0.082 परमाणु लीटर मोल की घात -1 K की घात -1। अतः सार्वत्रिक गैस नियतांक का मान 0.082 परमाणु लीटर मोल की घात -1 K की घात -1 है। मैक्सवेल बंटन फलन। गैस के दिए गए द्रव्यमान में सभी अणुओं के वेग समान नहीं होते, चाहे स्थूल प्राचल जैसे कि दाब, आयतन और ताप नियत हों। संघट्ट अणुओं की दिशा और गति परिवर्तित कर देते हैं। हालांकि साम्य अवस्था में चालों का वितरण नियत रहता है। बहुत से पिंडों के बने निकायों के व्यवहार का अध्ययन करते समय वितरण बहुत महत्वपूर्ण होते हैं। आणविक चालों का वितरण V तथा V प्लस dV चालों के बीच अणुओं की संख्या बताता है। V तथा V प्लस dV चालों के साथ अणुओं का अंश पट्टी के क्षेत्रफल के बराबर होता है। ऊर्जा के समविभाजन का नियम। ऊर्जा समविभाजन के नियम के अनुसार तापीय साम्यावस्था में किसी गतिशील निकाय के लिए कुल ऊर्जा सभी स्वतंत्र कोटियों में समान रूप से बंटित होती है और प्रत्येक अणु से प्रति स्वतंत्र कोटि संबद्ध ऊर्जा 1/2 kT होती है, जहां K बराबर बोल्ट्जमैन नियतांक, T बराबर निकाय का निरपेक्ष ताप, निकाय की स्वतंत्रता की कोटि। इसे स्वतंत्र निर्देशांकों की संख्या के रूप में परिभाषित किया जाता है, जो प्रणाली की स्थिति या विन्यास स्पष्ट करने के लिए आवश्यक होते हैं। एक निकाय की स्वतंत्रता कोटि की संख्या निम्न रूप में व्यक्त है। F बराबर 3n-a, जहां F बराबर स्वतंत्र कोटियों की संख्या, n बराबर एक अणु में परमाणुओं की संख्या, a बराबर एक अणु के परमाणुओं के बीच स्वतंत्र संबंधों की संख्या। ऊष्मा समविभाजन का नियम इस रूप में भी स्पष्ट किया जा सकता है कि नियतांक दाब तथा ताप पर किसी दी गई गैस के एक अणु की कुल औसत गतिज ऊर्जा इसकी सभी स्वतंत्र कोटियों के बीच समान रूप से बंटित होती है और प्रति स्वतंत्र कोटि प्रति अणु औसत गतिज ऊर्जा 1/2 kT होती है, जहां T बराबर गैस का तापमान है। विशिष्ट ऊष्मा धारिता। विशिष्ट ऊष्मा धारिता को नियतांक दाब पर किसी गैस की विशिष्ट ऊष्मा के नियतांक आयतन पर गैस की विशिष्ट ऊष्मा से अनुपात के रूप में परिभाषित किया जाता है। इसका मान गैस की परमाणुकता को प्रदर्शित करता है। एक परमाणु गैसें T तापमान तथा P ताप पर एक आदर्श एक परमाणु गैस के 1 मोल पर विचार करें। एक परमाणु गैस के लिए स्वतंत्रता कोटि की संख्या 3 होती है। ऊर्जा समविभाजन के नियम के अनुसार प्रति अणु प्रति स्वतंत्रता कोटि औसत गतिज ऊर्जा बराबर 1/2 kT। गैस के 1 मोल की औसत गतिज ऊर्जा बराबर kT गुणे n, जहां n बराबर आवोगाद्रो संख्या है, अतः U बराबर 3/2 RT, जहां U गैस के 1 मोल का Ke है। du/dt बराबर CV, CV बराबर 3/2 R, लेकिन Cp बराबर CV प्लस R। हम पाते हैं कि Cp बराबर 5/2 R, अतः Cp/CV बराबर 5/3। द्विपरमाणु गैसें। द्विपरमाणु गैस के लिए स्वतंत्रता कोटि की संख्या 5 है। Cp/CV बराबर 9/7। बहुपरमाणु गैसें। इसमें 3 स्थानांतरीय और 3 घूर्णी स्वतंत्रता कोटियां होती हैं। Cp/CV बराबर 4 + F/3 + F। Cp/CV बराबर R किसी भी आदर्श गैस के लिए सत्य है, चाहे वो एक परमाणुक, द्विपरमाणुक या बहुपरमाणुक हो। माध्य मुक्त पथ। किसी गैस के अणु सतत, त्वरित या यादृच्छिक गति की अवस्था में रहते हैं। इनमें परस्पर आदर्श प्रत्यास्थ संघट्ट होते हैं। संघट्टों के अतिरिक्त अणु एक दूसरे पर कोई बल नहीं आरोपित करते, इसलिए 2 क्रमिक संघट्टों के बीच चली गई दूरी नियतांक वेग के साथ एक सीधी रेखा होती है। एकल गैस अणु का पथ विभिन्न लंबाइयों वाले छोटे छोटे टेढ़े मेढ़े पथों की एक श्रृंखला से बनता है। ये पथ मुक्त पथ कहलाते हैं तथा इनके माध्य मुक्त पथ कहलाते हैं। लेमला बराबर KT बटे √2 पाई सिग्मा वर्ग P, जहां सिग्मा बराबर अणु का व्यास है, P बराबर गैस का ताप है, T बराबर गैस का ताप है, K बराबर वोल्टेजमैन नियतांक है। ब्राउनी गति। जल या वायु या किसी अन्य तरल में निलंबित सूक्ष्मदर्शीय आकार के कणों की सतत टेढ़ी मेढ़ी यादृच्छिक गति ब्राउनी गति होती है। ये परिघटना रॉबर्ट ब्राउन द्वारा खोजी गई थी तथा ये अणुगति सिद्धांत के आधार पर स्पष्ट की जाती है। ब्राउनी गति बढ़ जाती है जब निलंबित कण का आकार अधिक छोटा हो, माध्यम का तापमान बढ़ा दिया जाए, माध्यम की क्षणता कम हो, माध्यम का घनत्व कम हो। क्या आप जानते हैं, आधुनिक ऊष्मागतिकी के विकास के पूर्व यह विचार था कि ऊष्मा एक तरल है और इसलिए इसे कैलारिक कहा गया। पिंड इस तरल की एक निश्चित मात्रा धारण करने में समर्थ माने गए, इसलिए हम ऊष्माधारिता शब्द का उपयोग करते हैं, जिसे जोसेफ ब्लैक द्वारा 1750 के दशक में पहली बार खोजा और नामकरण किया गया। प्रत्येक अणु अपने निकटवर्ती अणुओं पर एक आकर्षण बल लगाता है जो अंतरा अणुक बल कहलाता है। मध्ययुक्त पथ की अवधारणा 1858 में प्रस्तुत की गई। जर्मन भौतिकविद रुडोल्फ क्लॉसियस ने इसे आणविक गति होने पर गैसीय पिंडों के पृथक अणुओं द्वारा चले गए पथों की माध्य लंबाई के रूप में परिभाषित किया। सारांश। आइए हमने जो कुछ सीखा है उसे संक्षेप में दोहराएं। अणुगति सिद्धांत इस विचार के आधार पर गैसों के व्यवहार की व्याख्या करता है कि गैसें तेजी से गति करने वाले परमाणुओं या अणुओं से बनी होती हैं। गैस का आयतन न केवल ताप पर बल्कि इस पर लगने वाले दाब पर भी निर्भर होता है। बॉयल के नियम के अनुसार ताप नियत रखने पर गैस के किसी दिए गए द्रव्यमान का ताप उसके आयतन के व्युत्क्रमानुपाती होता है। चार्ल्स के नियम के अनुसार किसी गैस का आयतन प्रत्येक 1 डिग्री सेल्सियस ताप परिवर्तन के लिए 0 डिग्री सेल्सियस पर इसके आयतन के गामा पी पर परिवर्तित होता है। यदि दाब स्थिर रखा गया हो तो गैस का दाब इसकी गतिज ऊर्जा प्रति इकाई आयतन के 2/3 के बराबर होता है। अणु की औसत गतिज ऊर्जा गैस की प्रकृति पर या अणु के द्रव्यमान पर निर्भर नहीं होती, ये केवल गैस के निरपेक्ष ताप पर निर्भर करता है। जल या वायु या किसी अन्य तरल में निलंबित सूक्ष्मदर्शीय आकार के कणों की सतत टेढ़ी मेढ़ी यादृच्छिक गति ब्राउनी गति होती है। विशिष्ट ऊष्माधारिता को नियतांक दाब पर किसी गैस की विशिष्ट ऊष्मा के नियतांक आयतन पर गैस की विशिष्ट ऊष्मा से अनुपात के रूप में परिभाषित किया जाता है।
Introduction. Today, physics teacher is going to perform an experiment in laboratory in front of students. He took a small balloon and put it in vacuum jar. Then he switches on the vacuum pump. Suddenly, the balloon starts to expand. After a while, he switches off the pump. Then, the balloon becomes in its original state. One student curiously asked, "Sir, will you please explain how this process works?" Sure, Varun. This is an example of kinetic theory. When the vacuum is turned on, the pressure exerted on the balloon decreases, and the balloon can expand until the vacuum jar is completely filled. And when the air is allowed back in the jar, the pressure is re-established and the balloon returns to its original volume. This shows an indirect relationship between pressure and volume. So students, today we learn more about the kinetic theory. Objectives. At the end of this lesson, you will be able to define kinetic theory, explain molecular nature of matter, understand behavior of gases, define Boyle's law and Charles' law, know kinetic theory of an ideal gas, calculate pressure of an ideal gas, analyze kinetic interpretation of temperature, know Maxwell distribution function, define law of equipartition of energy, calculate specific heat capacity, define mean free path and Brownian motion. Definition. The kinetic theory was developed in the 19th century by Maxwell, Boltzmann and others. Kinetic theory explains the behavior of gases based on the idea that the gas consists of rapidly moving atoms and molecules. This is possible as the interatomic forces, which are short-range forces that are important for solid and liquids, can be neglected for gases. Molecular nature of matter. All molecules of a gas are identical but differ from those of other gases. The molecules of a gas behave as perfect elastic spheres and are of very small size as compared to the separation between the molecules. All the molecules are always in random motion and they have velocities in all directions ranging from 0 to infinity. Molecules during their motion collide with each other and also collide with walls of the container. All these collisions are perfectly elastic. Molecules do not exert any force on each other except during collision. Molecules always move along a straight line between two collisions and the distance travelled between two successive collisions is called mean free path. Behavior of gases. All gases expand on heating. As far as changes in volume are concerned, the effect of pressure on solids and liquids is negligible. But gases can be compressed easily. They expand in volume even at constant temperature, provided the pressure is allowed to fall. The volume of a gas, therefore, not only depends on the temperature, but also on its pressure. Boyle's law. Boyle's law states that for a fixed mass of a gas, the volume varies inversely with its pressure provided the temperature remains constant. PV is equal to constant, where P is the pressure and V is the volume. It follows that if volume of the gas is reduced to 1/2, its pressure will be doubled. Energy of a gas at a constant temperature has a constant value and it does not increase or decrease with expansion or contraction of the gas so long as its temperature remains constant. A gas which obeys Boyle's law fully is known as perfect gas or an ideal gas. Boyle's law may be stated as, at constant temperature, the density of a gas increases directly with its pressure. P upon rho is equal to constant. Charles' law. Charles' law states that the volume of a gas changes by gamma P of its volume at 0 degrees centigrade for each 1 degree centigrade temperature change, provided the pressure remains constant. V is equal to V naught multiplied by 1 plus gamma P theta, where V is the volume at theta degrees Celsius and V naught is the volume at 0 degrees centigrade. The above relation can be written as V is equal to V naught multiplied by 1 plus theta upon 273. According to equation, a graph between volume and temperature is a straight line. An ideal gas obeys this equation throughout the entire range of temperature. Real gases obey the equation only at high temperatures. As the temperature is reduced, it starts deviating from the equation. Kinetic theory of an ideal gas. A gas consists of a large number of identical, tiny, spherical, neutral and perfectly elastic particles called molecules. In a gas, molecules are moving in all possible directions with all possible speeds. The space occupied by the molecules is negligible as compared to the volume of the gas. There is no force of attraction between the molecules. The collision between the molecules and with the walls of the container is perfectly elastic. The duration of collision is negligible compared with the time spent by a molecule between the collisions. Gravity has hardly any effect on the molecular motion as their mass is too small and speed is very high. Pressure of an ideal gas. Gas exerts pressure due to collision of its molecules with the walls of the container. Let us consider an ideal gas having n molecules, each of mass m, contained in a rectangular box of side Lx, Ly, Lz. Kinetic energy per unit volume is given by E is equal to half rho V RMS square. Pressure of the gas is given by P is equal to 2 by 3 of E. Hence, the pressure of a gas is equal to 2/3 of its kinetic energy per unit volume. Kinetic interpretation of temperature. Average kinetic energy of one molecule E is given by E is equal to Em upon N is equal to 3 RT upon 2N is equal to 3 kT by 2, where K is Boltzmann's constant. So, the average kinetic energy of a molecule does not depend on the nature of the gas or mass of the molecule. It means different gases at the same temperature have same total kinetic energy and same average kinetic energy per molecule. It depends only on the absolute temperature of the gas. Temperature can be interpreted as a measure of the average kinetic energy of the molecules of a gas. Example. Let's take an example of kinetic theory of an ideal gas. Using the ideal gas equation, PV is equal to RT. Calculate the value of universal gas constant. Let's see the solution. We have V is equal to 22,400 into 10 to the power minus 6 meter cube. T is equal to 273 Kelvin. PV is equal to RT. P is equal to HDG. Now, we calculate value of R by putting the values. R is equal to PV by T is equal to 2 calorie per mole per Kelvin. If V is equal to 22.4 liters, P is equal to 1 atmosphere, T is equal to 273 Kelvin, R is equal to 0.082 atom liter per mole per Kelvin. Hence, the value of universal gas constant is 0.082 atom liter per mole per Kelvin. Maxwell distribution function. In a given mass of gas, the velocities of all molecules are not the same, even when bulk parameters like pressure, volume, and temperature are fixed. Collisions change the direction and the speed of molecules. However, in a state of equilibrium, the distribution of speed is constant. Distributions are very important and useful when dealing with system containing large number of objects. The molecular speed distribution gives the number of molecules between the speeds v and v plus dv. The fraction of the molecules with speeds v and v plus dv is equal to the area of the strip. Law of equipartition of energy. Law of equipartition of energy states that for any dynamic system in thermal equilibrium, the total energy gets distributed equally amongst all the degrees of freedom, and the energy associated with each molecule per degree of freedom is half kT, where K is equal to Boltzmann's constant, T is equal to absolute temperature of the system. Degree of freedom of a system. It is defined as the number of independent coordinates which are required to explain the position or configuration of the system. The number of degrees of freedom of a system is given by F is equal to 3n minus A, where F is equal to number of degrees of freedom, n is equal to number of atoms in one molecules, A is equal to number of independent relations between the atoms of one molecule. Law of equipartition of energy can also be stated as the total average kinetic energy of a molecule of a given gas at a constant pressure and temperature is equally distributed among all its degree of freedom, and the average kinetic energy per molecule per degree of freedom is half kT, where T is equal to temperature of gas. Specific heat capacity. Specific heat capacity is defined as the ratio of the specific heat of a gas at constant pressure to the specific heat of a gas at constant volume. Its value represents the atomicity of gas. Monoatomic gases. Consider 1 mole of an ideal monoatomic gas at a temperature T and pressure P. The number of degrees of freedom of a monoatomic gas is 3. According to the law of equipartition of energy, average kinetic energy per molecule per degree of freedom is equal to half kT. Average kinetic energy of 1 mole of gas is equal to kT into n, where n is equal to Avogadro's number. Thus, U is equal to 3 by 2 RT, where U is the kinetic energy of 1 mole of gas. Du by dt is equal to CV. CV is equal to 3 by 2 R, but Cp is equal to Cv plus R. We get Cp is equal to 5 by 2 R. Hence, Cp by Cv is equal to 5 by 3. Diatomic gases. The number of degrees of freedom of a diatomic gas is 5. Cp by Cv is equal to 9 by 7. Polyatomic gases. It has 3 transitional and 3 rotational degrees of freedom. Cp by Cv is equal to 4 plus F upon 3 plus F. Cp minus Cv is equal to R is true for any ideal gas, whether monoatomic, diatomic or polyatomic. Mean free path. The molecules of a gas are in a state of continuous, rapid and random motion. They undergo perfectly elastic collisions against one another. The molecules exert no force on one another except during collisions. Therefore, the free path travelled between two successive collisions will be a straight line with constant velocity. The path of a single gas molecule comprises of a series of short zigzag paths of different lengths. These paths are known as free paths and their mean is called mean free path. Lambda is equal to kT upon root 2 pi sigma square p, where sigma is equal to diameter of the molecule, p is equal to pressure of the gas, T is equal to temperature of the gas, K is equal to Boltzmann's constant. Brownian motion. Brownian motion is the continuous zigzag random motion of particles of microscopic size suspended in water or air or some other fluid. This phenomenon was discovered by Robert Brown and is explained on the basis of kinetic theory. Brownian motion increases when size of suspended particle is smaller, temperature of medium is raised, viscosity of medium is smaller, density of medium is smaller. Did you know? Before the development of modern thermodynamics, it was thought that heat was a fluid and so-called caloric. Bodies were capable of holding a certain amount of this fluid. Hence, we term heat capacity, named and first investigated by Joseph Black in the 1750s. Each molecule exerts a force of attraction on its neighboring molecule, which is called the intermolecular force. The concept of mean free path was introduced in 1858 paper. on the mean length of the paths described by the separate molecules of gaseous bodies on the occurrence of the molecular motion by German physicist Rudolf Clausius. Summary. Let us summarize what we have learned. Kinetic theory explains the behavior of gases based on the idea that the gas consists of rapidly moving atoms and molecules. The volume of a gas not only depends on the temperature but also on its pressure. Boyle's law states that for a fixed mass of a gas, the volume varies inversely with its pressure provided the temperature remains constant. Charles' law states that the volume of a gas changes by gamma p of its volume at 0 degrees centigrade for each 1 degree centigrade temperature change, provided the pressure remains constant. The pressure of a gas is equal to 2/3 of its kinetic energy per unit volume. The average kinetic energy of a molecule does not depend on the nature of the gas or mass of the molecule. It depends only on the absolute temperature of the gas. Brownian motion is the continuous zigzag random motion of particles of microscopic size suspended in water or air or some other fluid. Specific heat capacity is the ratio of the specific heat of a gas at constant pressure to the specific heat of gas at constant volume.
परिचय। कल रॉय बहुत प्रसन्न था क्योंकि वो अपने परिवार के साथ एक पिकनिक पर जा रहा था। वे सभी सहज गति से यात्रा कर रहे थे कि अचानक उनके रास्ते में एक कुत्ता आ गया और उसके पिता ने तेजी से ब्रेक लगाए। उन सभी ने एक झटका अनुभव किया और वे आगे को गिर पड़े। तब राय ने अपने पिता से पूछा कि ब्रेक लगाए जाने पर हम सभी आगे की ओर क्यों गिर गए? तब उसके पिता ने उत्तर दिया कि यह हमारे शरीर के जड़त्व के कारण हुआ। इसका अर्थ है कि कार रुकने के समय शरीर अपने जड़त्व के कारण गतिमान रहा। आइए अब जड़त्व तथा गति के नियमों के बारे में और अधिक सीखें। उद्देश्य। इस पाठ के अंत में आप निम्न करने में सक्षम हो जाएंगे। अरस्तु की भ्रामकता को समझना, जड़त्व के नियम को परिभाषित करना, न्यूटन के गतियों के नियम को परिभाषित करना, आवेग को परिभाषित करना, संवेग संरक्षण के नियम को समझना, किसी कण की साम्यावस्था की गणना करना, यांत्रिकी में सामान्य बलों को समझना, वर्तुल यानी वृत्तीय गति को परिभाषित करना और यांत्रिकी में समस्याओं को हल करना। अरस्तु की भ्रामकता। यूनानी विचारक अरस्तु के अनुसार किसी वस्तु को गतिमान बनाए रखने के लिए एक बाह्य बल आवश्यक होता है। एक खिलौना गाड़ी विराम अवस्था में है। जब एक बालक गाड़ी से जुड़े हत्थे को पकड़कर खींचता है तो गाड़ी गतिमान हो जाती है और जब बालक गाड़ी का हत्था छोड़ देता है तो गाड़ी विराम अवस्था में आ जाती है। अब अरस्तु के अनुसार गाड़ी इसलिए विराम अवस्था में आ जाती है क्योंकि इस पर कोई बाह्य बल नहीं लग रहा है, लेकिन वास्तव में गाड़ी इसलिए विराम अवस्था में आ जाती है क्योंकि पृष्ठ से लगने वाला घर्षण बल गाड़ी की गति का प्रतिरोध करता है। जड़त्व का नियम। किसी वस्तु का जड़त्व उसका वह गुण होता है जिसके द्वारा ये अपनी विराम अवस्था में परिवर्तन का या किसी बाह्य बल की अनुपस्थिति में वस्तु की एक समान गति का प्रतिरोध करती है। किसी वस्तु का जड़त्व इसके द्रव्यमान के अनुक्रमानुपाती होता है। किसी वस्तु का वेग तब तक निश्चित रूप से बना रह सकता है जब तक उस पर कोई त्वरण या मंदन कार्य ना करे। ऐसी दशा केवल समतल तलों पर प्राप्त की जाती है जहां घर्षण के बल को न्यून किया जाता है। आइए एक उदाहरण देखें। नीचे को ढाल युक्त तल की स्थिति में त्वरण का एक कारण पहले से उपस्थित रहता है। ऊपर को ढाल युक्त तल की स्थिति में मंदन का एक कारण पहले से उपस्थित रहता है। क्षैतिज तल की स्थिति में नियत गति होती है। न्यूटन का गति का प्रथम नियम। न्यूटन के गति के प्रथम नियम के अनुसार प्रत्येक पिंड तब तक अपनी विराम अवस्था या सरल रेखा में एक समान गति की अवस्था में रहता है जब तक कि कोई बाह्य बल उसे अन्य रूप में व्यवहार करने के लिए बाध्य नहीं करता। यदि किसी वस्तु पर नेट बाह्य बल शून्य हो तो इसका त्वरण शून्य होगा। वस्तु पर नेट बाह्य बल न होने की स्थिति में त्वरण शून्य नहीं हो सकता। न्यूटन का गति का द्वितीय नियम। पहले हम सभी संवेग के बारे में बात करेंगे। किसी वस्तु का संवेग इसके द्रव्यमान तथा वेग के गुणनफल के रूप में व्यक्त किया जाता है। P बराबर m गुणा v। ये एक सदिश राशि है। संवेग की दिशा वेग की दिशा में होती है। इसका SI मात्रक किलोग्राम मीटर प्रति सेकंड होता है। न्यूटन का गति का द्वितीय नियम कहता है कि किसी पिंड पर कार्य करने वाला नेट बाह्य बल इसके संवेग परिवर्तन की दर के अनुक्रमानुपाती होता है। इसका समीकरण निम्न रूप में दिया गया है। u मीटर प्रति सेकंड के वेग से आरंभ में गतिमान m द्रव्यमान के एक पिंड पर विचार करें, जिस पर F न्यूटन का बल लगाए जाने पर t समय के बाद इसका वेग v मीटर प्रति सेकंड हो जाता है। तब न्यूटन के द्वितीय नियम के अनुसार F बराबर mv घटा mu बटे t। F बराबर ma, जहां a पिंड में उत्पन्न त्वरण है। अतः पिंड पर कार्य करता नेट बाह्य बल इसके द्रव्यमान तथा इसमें उत्पन्न त्वरण के गुणनफल के बराबर होता है। उदाहरण। आइए न्यूटन के गति के द्वितीय नियम का एक उदाहरण देखें। एक 8 किलोग्राम द्रव्यमान पर कार्य करता नियत बल 25 सेकंडों में इसकी चाल को 2 मीटर प्रति सेकंड से 3.8 मीटर प्रति सेकंड में बदल देता है। यदि पिंड की गति की दिशा अपरिवर्तित रहे तो बल के परिमाण एवं दिशा की गणना करें। आइए इसका हल देखें। दिए गए मान हैं m बराबर 8 किलोग्राम, u बराबर 2 मीटर प्रति सेकंड, v बराबर 3.8 मीटर प्रति सेकंड, t बराबर 25 सेकंड, f बराबर ma बराबर m v घटा u बटे t बराबर 8 3.8 घटा 2 बटे 25। बल बराबर 0.58 न्यूटन। क्योंकि गति की दिशा में परिवर्तन नहीं हुआ है बल्कि वेग का परिमाण बढ़ा है, इसलिए बल गति की दिशा में ही कार्यरत होगा। आवेग। आवेग को किसी पिंड पर एक अल्प समय काल के लिए कार्य करने वाले बल के प्रभाव के रूप में परिभाषित किया जाता है। आवेग बल तथा समय अंतराल के गुणनफल के बराबर होता है। I बराबर F गुणा T। यदि पिंड का संवेग T समय में P1 से P2 परिवर्तित होता है तो न्यूटन के गति के द्वितीय नियम के अनुसार F बराबर P2 घटा P1 बटे T। आवेग I बराबर P2 घटा P1 बटे T गुणे T। I बराबर P2 घटा P1। I बराबर डेल्टा P। आवेग पिंड के संवेग में परिवर्तन के भी बराबर होता है। यह एक सदिश राशि है तथा इसकी दिशा संवेग में परिवर्तन के समान होती है। न्यूटन का गति का तृतीय नियम। न्यूटन के गति के तृतीय नियम के अनुसार प्रत्येक क्रिया की सदैव समान एवं विपरीत प्रतिक्रिया होती है। क्रिया और प्रतिक्रिया का परिमाण समान होता है, दिशाएं विपरीत होती हैं और वे भिन्न पिंडों पर कार्य करती हैं। पतवार की सहायता से एक नाव खेता व्यक्ति भूमि पर उछलती गेंद न्यूटन की गति के तृतीय नियम के उदाहरण हैं। पिंडों ए और बी के एक युग्म पर विचार करें, तब एफ ए बी बराबर घटा एफ बी ए। दोनों पिंडों के बीच अंतर क्रिया में संलग्न दो बलों में से एक क्रिया बल कहा जा सकता है, दूसरे बल को प्रतिक्रिया बल कहा जा सकता है। संवेग का संरक्षण। वियुक्त निकाय। किसी निकाय को वियुक्त कहा जाता है यदि निकाय व परिवेश के बीच द्रव्यमान तथा ऊर्जा का कोई विनिमय नहीं हो। संवेग संरक्षण के अनुसार किसी बाह्य बल की अनुपस्थिति में किसी वियुक्त निकाय का कुल रैखिक संवेग समान या संरक्षित बना रहता है। न्यूटन के गति के द्वितीय नियम के उपयोग द्वारा व्याख्या। जहां कोई बाह्य बल नहीं है, F बराबर 0, तो dp बटे dt बराबर 0। P बराबर स्थिरांक, mv बराबर स्थिरांक, m1v1 बराबर m2v2। न्यूटन के गति के तृतीय नियम के उपयोग द्वारा व्याख्या। m1 तथा m2 द्रव्यमानों के दो कणों से बने एक वियुक्त निकाय पर विचार करें। निकाय का कुल द्रव्यमान है m बराबर m1 जमा m2। माना कि निकाय पर एक बल F प्रयुक्त किया गया है, जिसके कारण m1 और m2 पर क्रमशः F1 और F2 कार्य करते हैं। यदि वियुक्त निकाय पर कार्य करने वाला कोई बाह्य बल नहीं है, F बराबर 0, d बटे dt, P बराबर 0, P बराबर स्थिरांक, अतः रैखिक संवेग के संरक्षण का नियम सिद्ध होता है। किसी कण की साम्यावस्था। जब किसी पिंड जिस पर बल कार्य करता है उसकी विरामावस्था या एक समान गति की अवस्था में कोई परिवर्तन नहीं होता है, तो वो पिंड साम्यावस्था में कहलाता है। संगामी बल वे बल होते हैं जिनकी क्रिया रेखाएं एक सार्वनिष्ठ बिंदु पर प्रतिच्छेद करती हैं। आकृति में 4 संगामी बल F1, F2, F3 तथा F4 दर्शाए गए हैं, जिनकी क्रिया रेखाएं O पर प्रतिच्छेद करती हैं। साम्यावस्था में कोई पिंड विरामावस्था में भी हो सकता है और नहीं भी हो सकता है। संगामी बलों की क्रिया के अंतर्गत किसी पिंड के साम्यावस्था में होने के लिए अनिवार्य शर्त यह है कि कार्य करने वाले सभी बलों का सदिश योग 0 होना चाहिए। लेमी का नियम। यदि किसी पिंड पर कार्यरत 3 संगामी बल इसे साम्यावस्था में रखते हैं, तो प्रत्येक बल अन्य 2 बलों के बीच के कोण की ज्या के समानुपाती होता है। माना कि F1, F2 तथा F3 साम्यावस्था में 3 संगामी बल हैं, तब लेमी के नियम के अनुसार F1 बटे साइन अल्फा बराबर F2 बटे साइन बीटा बराबर F3 बटे साइन गामा। यांत्रिकी में सामान्य बल। यांत्रिकी में हमारा सामना अनेक प्रकार के बलों से होता है। यांत्रिकी में मुख्य संपर्क बल घर्षण कहलाता है। घर्षण, इसे एक विरोधी बल के रूप में परिभाषित किया जाता है जो संपर्क वाले 2 पृष्ठों के बीच तब उत्पन्न होता है जब एक पिंड अन्य पिंड के पृष्ठ पर सरकती या लुढ़कती है या ऐसा करने के लिए प्रवृत्त होती है। ये दोनों पिंडों के संपर्क पृष्ठों पर स्पर्श रेखीय कार्य करता है तथा न्यूटन के गति के तृतीय नियम का पालन करता है। सीमित घर्षण। संपर्क में 2 पिंडों के बीच घर्षण का बल जब एक पिंड अन्य पिंड के पृष्ठ पर सरकना शुरू करने की स्थिति में होता है। स्थैतिक घर्षण, संपर्क में दो पिंडों के बीच घर्षण का बल जो उससे पूर्व होता है जब वास्तव में कोई पिंड किसी अन्य पिंड के पृष्ठ पर चलना शुरू करता है। गतिज घर्षण, संपर्क में दो पिंडों के बीच घर्षण का बल जब एक पिंड अन्य पिंड के पृष्ठ पर गतिमान होता है। लोटनी घर्षण, इसे ऐसे घर्षण के रूप में परिभाषित किया जाता है जो तब उपस्थित होता है जब पिंड जैसे कि वलय, चकती, गोला या बेलन अन्य पिंड के पृष्ठ पर लुढ़कते हैं या ऐसा करने को प्रवृत्त होते हैं। लोटनी घर्षण सर्पी घर्षण से कम होता है। घर्षण एक अनिवार्य बुराई है। घर्षण सदैव गति का विरोध करता है और घर्षण से छुटकारा पाने के लिए ऊर्जा व्यय होती है, लेकिन साथ ही ये अनिवार्य भी है क्योंकि ये हमें चलने, वस्तुओं को चलाने तथा शक्ति का प्रेषण करने में सहायता प्रदान करता है। घर्षण कम करने के उपाय। दो संपर्क पृष्ठों के बीच घर्षण गुणांक का मान कम करते हुए घर्षण को घटाया जा सकता है। इसे निम्नांकित तरीकों से किया जा सकता है: पॉलिश करके, ल्यूब्रिकेंट्स के उपयोग द्वारा चिकना करके, सर्पी को लोटनी में परिवर्तित करके। वृत्तीय या वर्तुल गति। जब कोई पिंड किसी वृत्ताकार पथ पर चलता है तो इसकी गति वृत्तीय गति कहलाती है, और यदि कोई पिंड किसी वृत्तीय पथ पर नियतांक चाल से घूमता है तो इसकी गति एक समान वृत्तीय गति कहलाती है। पिंड पर पल